James Webb stared at a single patch of sky and found a wall of galaxies so enormous it should be physically impossible. Spanning 1.3 billion light-years, it formed when the universe was barely 300 million years old. Our best models of physics say a structure that size simply cannot exist that early. And yet, there it is. We are going to walk through what Webb found, why it breaks the rules, and what it means for everything we thought we understood about how the universe was built. If you enjoy the journey, a like and subscribe keeps us going. Now, prepare yourselves. We begin. You have probably seen the images. Thousands of galaxies packed into a patch of sky the size of a grain of sand, held at arm's length. Colors that feel almost too vivid to be real. But those images are not art. They are data. And the instrument that captured them works in a way no telescope before it ever could. Every telescope ever built before Webb was chasing visible light. The kind your eyes detect. The kind that bounces off a wall when you flip a switch. Hubble was brilliant at it, but visible light has a problem. Space stretches it. Here is what that means. When a galaxy sits far enough away, the universe itself is expanding between you and it. That expansion pulls the light waves apart, like stretching a rubber band with a wave drawn on it. The wave gets longer. Longer light waves shift toward red. Stretch them far enough, and they slide completely out of the visible spectrum, into infrared. To your eyes and to Hubble, that galaxy simply disappears. It goes dark. It becomes invisible, not because it stopped shining, but because the light arrived in a language older telescopes could not read. Webb reads that language fluently. Its primary mirror spans 21 feet across, made of 18 gold-coated hexagonal segments that fold like origami for launch and open in space. Gold reflects infrared better than any other coating. Every design choice, the mirror shape, the size, the sunshield the size of a tennis court blocking heat from the star we orbit, was built around one goal: catch the oldest, most stretched light in the universe. And the oldest light comes from the oldest structures. When Webb locks onto a distant region of sky, it is doing something that sounds simple, but is genuinely staggering. It is looking backward in time. Light takes time to travel. The light Webb catches from a galaxy 13 billion light-years away left that galaxy 13 billion years ago. Webb is not seeing what that galaxy looks like now. It is seeing what it looked like when the universe was barely a few 100 million years old. A photograph from the universe's childhood. Hubble gave us glimpses of that era. Blurry, faint, frustrating glimpses. Webb gives us sharp images with spectral data, meaning it can break the light apart into its components, like a prism, and read the chemical fingerprints of what those ancient galaxies are made of, how fast they are moving, and how massive they are. That capability is where everything starts to go wrong for our models. Because Webb was designed to confirm what we expected to find in the early universe: small, chaotic, proto-galaxies just beginning to form, scattered seeds of structure, not yet organized into anything grand. Scientists expected the early universe to look like a rough draft. Instead, Webb found finished buildings in a construction zone, galaxies far too large, far too bright, and far too organized for their age. And then, in one particular field of observation, something that made researchers go quiet in front of their screens. A structure so enormous, it rewrote the conversation entirely. Before we get to that structure, you need to understand the rules it broke. Because the rules were not guesses. They were the product of a century of mathematics, observation, and cosmological theory. A framework so solid that most physicists treated it the way you treat the ground beneath your feet. And the ground just cracked. The field of sky Webb was pointed at had a name, a catalog number, a set of coordinates. Astronomers had looked in that direction before. Other telescopes had swept past it. Nothing dramatic had ever turned up. It was, by all reasonable expectations, an ordinary slice of the universe. That is exactly why they chose it. When you are trying to understand the universe as a whole, you sample random regions. You point your telescope somewhere generic, somewhere without a known dramatic object nearby to contaminate your data, and you see what a typical piece of the cosmos looks like. Cosmologists call these deep fields. Hubble made its most famous images this way. staring at blank patches of sky for days, until the faintest light accumulated on the detector. Webb did the same, but deeper, longer exposures, sharper resolution, and with that infrared sensitivity that could peel back layers of cosmic time no prior instrument had reached. The observation campaign was designed around a specific scientific question. Scientists wanted to understand how galaxies cluster together at extreme distances. Galaxy clustering is not random. Gravity pulls things together over time, and the patterns those clusters form carry a record of how matter was distributed in the very early universe. Study the clusters, and you read the history. Standard cosmology had clear predictions. At distances corresponding to the universe's first few 100 million years, clusters should be small, loose associations of young galaxies, barely gravitationally bound, just starting to find each other across the void. A few dozen galaxies here, a few dozen there. Maybe, at the extreme end of predictions, a modest protocluster a few 100 million light-years across. The team pointed Webb at the field. The exposure ran. The data came back to Earth and went through processing. And then the maps appeared. Researchers were looking for small clusters. What the maps showed was a continuous chain of galaxies, stretching across a distance so large, the team initially assumed they had made an error. The structure appeared to span over 1 billion light-years from end to end, in a universe that had only existed for a few 100 million years at the time that structure formed. One of the first things scientists do when data looks impossible is check the instruments. Then they check the calibration. Then they check the data reduction pipeline, the software that converts raw detector signals into images and maps. Every check came back clean. The telescope was working perfectly. The structure was real. And it gets stranger when you understand the light arriving from those galaxies. Because Webb's spectral analysis, its ability to read the chemical fingerprints of each galaxy, confirmed they all sat at the same distance from us. The same cosmic moment. These were galaxies that existed simultaneously, linked across an impossible span, in an era when the universe was still a newborn. A structure 1 billion light-years wide, confirmed real, sitting in a universe that had barely had time to breathe. The question that followed was simple and terrifying. How? Our best physics said this was more than improbable. It said this was a structural violation, like watching a skyscraper finish construction before the concrete had time to dry. Except the concrete in question is the fundamental gravitational physics that governs how matter assembles across cosmic time. To understand exactly why the size of this thing is so alarming, you need to know the rules. The rules cosmologists spent a century building, and they are stricter than you might think. The data did not announce itself with alarms. There were no flashing warnings on a screen, no automated system flagging an anomaly. The realization came the way most scientific shocks do. Slowly, then all at once. A researcher was mapping the redshift values of galaxies in the field. Redshift is the number that tells you how far away a galaxy is, derived from how much its light has been stretched by the universe's expansion. Each galaxy in the dataset had its own value, and as the researcher plotted them, something strange emerged in the distribution. A cluster of galaxies all shared nearly identical redshift values. That alone is not unusual. Groups of galaxies often sit at similar distances. But the number of galaxies sharing that value kept growing as more data came in. Dozens became scores, scores became hundreds, and when the team began mapping their physical positions in three-dimensional space, the shape that appeared was not a cluster. It was a wall, a continuous filament or sheet of galaxies stretching in one direction across the mapped field, so elongated and so densely populated that it looked deliberate, like something had drawn a line across the early universe and filled it with light. The lead researchers pulled in colleagues. Maps were redrawn. The structure held. Spectroscopic confirmation, the gold standard in astronomy where you verify distance by reading the actual chemical light signatures of each galaxy individually, was run on hundreds of objects in the structure. The results kept agreeing with each other. These galaxies were all real, all at the same distance, all part of the same enormous arrangement. Then came the size calculation. When you know the redshift of a galaxy, and you know the expansion history of the universe, you can calculate the physical distance that corresponds to that redshift. The team ran those numbers across the full extent of the structure, The result came out at over 1.3 billion light-years in its longest dimension. For a moment, go somewhere quiet and try to picture 1 light-year. Light travels at about 5.9 trillion miles in a single year. 1 light-year is that distance. 1.3 billion of them, laid end to end, is the span of this structure. And this structure existed when the universe was roughly 300 million years old. The room got very quiet, because every scientist in that room knew the same thing. The universe at 300 million years old did not have enough time to build something that size. Gravity is patient. It pulls matter together slowly. The calculations governing how long it takes for gravity to assemble structures of various sizes are well established, tested across decades of observation. A structure 1.3 billion light-years across requires far longer than 300 million years to form under normal gravitational physics. The team began writing the paper carefully. They checked their assumptions. They checked the cosmological model they were using to calculate physical distances. They consulted the redshift distance relationship that underpins modern astronomy. Every check confirmed the same answer. The structure formed faster than physics said was possible. What you are about to understand is why that is so disturbing. Because the rules this structure broke were not minor footnotes. They were the load-bearing walls of cosmology. Zoom out far enough from any galaxy, far enough that individual stars dissolve into faint smears, and the universe stops looking random. A pattern emerges. Galaxies do not float independently through empty space. They gather along thin threads and flat sheets, surrounding vast empty bubbles that contain almost nothing. Scientists call this arrangement the cosmic web. Picture a foam, the kind you see on a wave at the beach or inside a slice of bread. Now imagine that foam frozen in 3 dimensions and scaled up to fill the entire observable universe. The walls of the bubbles are where the galaxies live. The insides of the bubbles are nearly empty. The places where multiple bubble walls meet form dense knots where the most massive galaxy clusters sit. This structure is real, confirmed, mapped extensively. The largest survey of its kind, completed over decades by teams across multiple continents, charted hundreds of millions of galaxies, and showed exactly this pattern at the scales reachable by older telescopes. The cosmic web is beautiful. It is also deeply meaningful, because it did not form by accident. The web grew from the universe's first moments. When the universe was very young, matter was distributed almost perfectly evenly. Almost. There were tiny ripples, fluctuations in density so small they would be invisible to any detector you could hold in your hand. But those tiny ripples mattered enormously. Over hundreds of millions of years, the slightly denser regions pulled in surrounding matter through gravity. The slightly emptier regions lost material to their denser neighbors. Over time, that gentle process amplified the ripples into walls, filaments, and voids. The web grew from whispers. The key word in that process is time. The web we see around us today, in the relatively nearby universe, took billions of years to develop its current complexity. The further back you look, the simpler the web should appear. Younger universe, less time for gravity to work, smaller structures. Every simulation ever run of cosmic structure formation agrees on this. You feed in the initial conditions from the Big Bang. You run the physics of gravity and expansion forward through time. And the web that grows matches what telescopes see in the nearby universe, almost perfectly. The match between simulation and observation is one of the great triumphs of modern cosmology, which is why what Webb found broke something more than just a size record. A structure over 1 billion light-years wide appearing in the early universe does not just mean one large thing formed unexpectedly. It means the web was already complex, already organized at enormous scales, at a time when the simulations show only the earliest, faintest hints of structure beginning to coalesce. The simulations and the observations are no longer agreeing, and when simulations built on the bedrock equations of physics stop matching what telescopes actually see, one of 2 things is true. Either the observations are wrong, or the physics is incomplete. The observations have been checked, repeatedly, by independent teams, using independent methods. So the question shifts, and it is heavier than it sounds. What is the physics missing? Something seeded the early universe with structure, at a scale and speed our models cannot account for. And to understand just how far outside the allowed range this structure sits, you need to know exactly where cosmologists drew the line. Cosmology has rules, precise mathematically derived limits on how large a coherent structure can grow within a given amount of time. These limits come from a straightforward piece of physics. Information cannot travel faster than light. That constraint matters more than it might seem. When gravity pulls matter together to form a structure, different parts of that structure need to be in gravitational communication. One end of the structure needs to have felt the gravitational influence of the other end. And gravitational influence travels at the speed of light. So in a universe that has existed for a certain length of time, gravity can only have connected regions within a certain distance of each other. Cosmologists call this the particle horizon. It is the boundary of the observable universe at any given moment in cosmic history. 2 points in space that are further apart than the particle horizon have never been in causal contact. They have never exchanged so much as a single photon. They are, in the most fundamental sense, strangers to each other. In the early universe, that horizon was small. The universe was young. Light had not had time to travel far. Gravity had not had time to bridge large distances, so structures were small. By the time the universe was 300 million years old, the particle horizon sat at a distance of roughly 300 million light-years. That is the hard ceiling. Two regions further apart than 300 million light-years at that moment in history had zero gravitational knowledge of each other. They could not have organized themselves into a shared structure. A structure 1.3 billion light-years wide exceeds that horizon by a factor of 4. Read that again. The structure Webb found is 4 times wider than the maximum distance over which gravity could have acted in the time available. 4 points in that structure, one at each corner, would have had no gravitational contact with each other, no shared signal, no common cause, and yet they form a coherent, connected arrangement. Galaxies lined up, distributed in a specific pattern, sharing the same moment in cosmic time. The analogy that helps: imagine 4 people are placed in 4 separate rooms with no way to communicate. You tell them each to draw a shape on a piece of paper, independently, with no contact. You collect the drawings, and all 4 have drawn the exact same shape. Your first thought is not coincidence. Your first thought is that somewhere, before they were separated, there was a blueprint. Something gave the early universe a blueprint at scales larger than the physics of causality should allow. And this is not a soft discrepancy, a slight overshoot of a fuzzy boundary. 4 times the allowed size is a structural emergency for standard cosmology. Some researchers looked at the result and immediately thought of a single candidate: inflation. The theory that the universe expanded at incomprehensible speed in its first fraction of a second, potentially stretching quantum-scale patterns into enormous cosmic structures before any of the normal rules of growth applied. But inflation was supposed to smooth things out, erase structure, make the universe uniform, unless something went wrong with inflation, or unless inflation was never quite what we thought. The structure has a name assigned by the team that found it, a catalog designation. But names matter less than dimensions. So here are the dimensions. Confirmed length, over 1.3 billion light-years. Confirmed existence, at a redshift placing it in the universe's first 300 million years. Confirmed method, spectroscopic analysis of hundreds of individual galaxies, each independently verified, all showing the same cosmic timestamp. Scientists call structures shaped like this a big ring, or in related discoveries announced around the same period, a giant arc. Webb and associated ground-based follow-up observations have revealed multiple candidates for structures at or near this scale in the early universe. The one in focus here is among the most extreme, and the confirmation behind it is among the most rigorous. Stand next to the Milky Way, the galaxy you live inside, and it spans roughly 100,000 light-years across. The structure Webb found is 13,000 times wider than your entire home galaxy. If the Milky Way were a single brick, this structure would be a wall stretching 13,000 bricks long. The galaxies inside it are dense, packed along the filament in concentrations that match what you see in well-developed structures in the nearby, much older universe. That density is part of what makes the discovery alarming. Dense filaments take time to develop. Matter has to flow in from surrounding space, drawn by gravity, accumulating over billions of years until the filament reaches the kind of density Webb is recording. 300 million years is nowhere near enough time for that accumulation under standard gravitational physics. The team that confirmed the structure ran their results through every cosmological model currently in use. None of them could reproduce it. Feeding the known initial conditions of the universe into the best simulations available, running the physics forward, you never get a structure this large at this earlier time. The simulations produce hints of proto-structure, the first faint seeds of filaments, never a completed, dense 1.3 billion light-year wall. A researcher on the confirmation team described the result in a published paper as sitting at the extreme limit of what standard cosmology could even theoretically allow, and possibly beyond it. That is, careful, academic language for "this should not be here." Here is the detail that separates this from a mere record breaker. Every previous largest structure discovery in modern cosmology caused excitement and debate, but each time, after scrutiny, the structure could be squeezed into the edges of existing models. Uncomfortable, but survivable. This one is producing a different reaction in the community, because the margin of violation is too wide to absorb quietly. 4 times the allowed scale, impossible density for its age, and existing in a region of sky that was chosen precisely because it was supposed to be ordinary. The universe hid its most rule-breaking secret in the most boring-looking corner of the sky. Now consider what this means for the 2 billion-year process that was supposed to have built it. Because even if you grant every favorable assumption in the physics, even if you squeeze the timelines, the mass budget, the gravitational constants, nothing comes close to explaining how this assembled in 300 million years. Something else was at work in the early universe, something the standard model never accounted for. And the candidates, when you lay them out, will make this feel even stranger. When astronomers talk about the early universe, they talk in redshift numbers. A redshift of 1 means the light you are catching has had its wavelength doubled by cosmic expansion. A redshift of 10 means the wavelength has stretched to 11 times its original length. The galaxies inside the structure Webb found sit at redshifts between approximately 6 and 7. That places them in a specific confirmed period of cosmic history. The universe at that moment was 300 million years old. To appreciate why that number is catastrophic for standard models, you need to feel the timeline. The Big Bang happened 13.8 billion years ago. Earth formed 4.5 billion years ago. The dinosaurs died 66 million years ago. 300 million years ago, Earth existed, but it was unrecognizable. The first land animals were just beginning to crawl out of the oceans. 300 million years sounds long by human terms. By cosmic terms, it is a heartbeat. The universe at that age had barely finished producing its first stars. The era of reionization, when the first stars lit up and began burning away the fog of neutral hydrogen that had filled space since the Big Bang, was only just getting underway. The universe was still, in large sections, dark. A sea of hydrogen and helium just starting to feel the pull of the first gathering masses. Structure formation, the process of matter organizing under gravity, had barely begun. Cosmological models agree on a rough sequence. In the first 100 million years, tiny density fluctuations begin to amplify. Small clumps of dark matter form first, because dark matter does not interact with light and can begin collapsing earlier. Ordinary matter slowly falls into those dark matter clumps. Over hundreds of millions of years, those clumps grow, merge, attract more material. By the time 1 billion years have passed, modest protoclusters exist. By a few billion years, the first true large-scale filaments are beginning to form. 300 million years into that sequence, you are still in the opening act, and yet the structure Webb found shows the kind of organization, density, and scale that models predict should take several billion years to develop. Researchers who work on structure formation timelines have calculated how long a filament of that density and length would need under standard physics. The estimates cluster around 3 to 5 billion years minimum. That means the structure exists somewhere between 2.7 and 4.7 billion years before it should. A simple analogy: imagine watching a time-lapse video of a city being built, and in the first 30 seconds of the video, a fully constructed skyscraper appears. No foundation being poured, no steel going up floor by floor, just the finished building standing there at a moment when the surrounding land still looks like raw earth. The skyscraper either broke physics, or the city has a history that predates the video. Scientists are now asking whether the universe has a history that predates what we thought was the beginning. Whether conditions existed before or during the Big Bang that laid down structure at scales standard inflation theory never anticipated. And that question leads somewhere genuinely unsettling. For most of human history, we had no idea where we were. The Earth was the center of everything. Then it became one planet among several around a star. Then one star among hundreds of billions in a galaxy. Then one galaxy among hundreds of billions more. In 2014, scientists added another layer to that list. And it was humbling. A team of researchers mapped the gravitational flows of galaxies in our local region of the universe. Not just the positions of galaxies, but the direction they were moving, the way they were being pulled by gravity, which structures were attracting which. What emerged from that mapping was a picture of a supercluster, a structure of interconnected galaxy clusters, all sharing a common gravitational basin, a region of space so large that everything inside it, including the Milky Way, is slowly drifting toward its gravitational center. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light-years. It contains the mass of approximately 100 million billion stars. The Milky Way sits in a quiet outskirt, far from Laniakea's dense core. Our nearest large galactic neighbor, the Andromeda Galaxy, is also inside Laniakea's boundaries. So is the Virgo cluster, a dense region of thousands of galaxies about 54 million light-years from us. When Laniakea was announced, it was the largest confirmed structure humans had ever mapped that contained our own address. 500 million light-years felt enormous. It was the kind of scale that requires effort to even attempt to imagine. Now compare it to the structure Webb found. Laniakea at 500 million light-years fits inside the Webb structure, with room left over. The structure Webb found is more than twice as wide as the supercluster we live in. And Laniakea formed over billions of years, in a universe with enough time to build something of that complexity. The Webb structure formed in a fraction of that time, in a universe still figuring out how to make stars. There is something quietly staggering about this comparison. The structure you live inside, the gravitational basin that defines your cosmic address, would be swallowed by a structure that formed when the universe was barely getting started. And Laniakea is confirmed to be one of the largest structures in the nearby universe. It already pushed the boundaries of what standard cosmology was comfortable explaining. Researchers at the time noted it sits near the theoretical maximum size for a gravitationally bound structure. The Webb structure does not sit near any maximum. It exceeds every maximum ever proposed. What does it mean for humanity? It means the scale of organized structure in the universe is larger and arrived earlier than a century of careful science predicted. The maps we drew of our cosmic neighborhood were correct. They were just a fraction of the full picture. And the full picture, as Webb keeps showing us, is stranger than the maps suggested. The Big Bang is not an explosion in the way most people picture it. An explosion happens inside space, with debris flying outward from a center point. The Big Bang was space itself expanding, carrying everything within it along for the ride. There was no center. There was no edge. Every point in the universe was, and remains, the origin point. In the first fractions of a second, the universe was unimaginably hot and dense. Everything was compressed into a state of pure energy, a seething plasma so hot that atoms could not form. Particles collided and annihilated each other continuously. Space expanded at a rate beyond description. As expansion continued, the universe cooled. After about 3 minutes, protons and neutrons combined into the first atomic nuclei. After roughly 380,000 years, the universe cooled enough that electrons could attach to nuclei and form the first neutral atoms, mostly hydrogen and helium. At that moment, the universe became transparent. Light could travel freely. That light is still traveling today, and we detect it as the cosmic microwave background, a faint glow covering the entire sky in every direction. The cosmic microwave background is the baby photo of the universe, and it is almost perfectly smooth. Scientists have mapped that background in extraordinary detail. Satellites have measured its temperature across the entire sky with precision down to millionths of a degree. And what those maps show is a universe that was, at 380,000 years old, almost perfectly uniform in temperature and therefore in density. Almost, not quite. There are tiny variations, regions that were 100,000th of a degree warmer or cooler than the average. Those tiny variations are the seeds. The slightly warmer spots correspond to regions slightly denser than average. Slightly denser regions had slightly stronger gravity. Over time, that stronger gravity pulled in more material. The seeds grew. The cosmic web we see today grew from those seeds. The mathematics of how those seeds grow is well understood. Physicists have equations that describe how density variations evolve over time. Those equations predict a specific maximum size of structure at any given moment in cosmic history. At 300 million years, the allowed maximum is clear. Structures of the size Webb found exceed it by a factor of 4. The Big Bang's almost perfect smoothness should have set strict limits on how far structure could emerge. The seeds were too small, too gentle, too evenly spaced to produce something that enormous that quickly. Unless the seeds were bigger in some places. Unless the initial conditions were less uniform than the cosmic microwave background suggests. Unless something happened between the Big Bang and the moment Webb is observing that added energy or organization to the system. And here is the detail that keeps theorists awake. If the initial conditions were different enough to produce this structure, they should also leave marks in the cosmic microwave background. Marks we would have detected. Marks that are not there. The universe is hiding something. It produced a structure that required different starting conditions than the ones it appears to have had. And right now, no one has a clean explanation for how. Gravity is the architect of the universe. Every galaxy, every cluster, every filament of the cosmic web exists because gravity had time to work. But gravity is slow, patient, methodical in a way that makes geological timescales feel frantic. Here is how structure formation actually works on the cosmic scale. A region of space begins with slightly more mass than its surroundings. That extra mass creates slightly stronger gravity. Surrounding matter begins to drift inward, slowly, drawn by the difference. As matter accumulates, the gravity strengthens. More material falls in. The clump grows. This process is called gravitational collapse, and its timescale depends entirely on how dense the initial region is. For the tiny density fluctuations present in the early universe, the growth is extraordinarily slow. Models show that in the first few 100 million years, the density contrast between the densest regions and the surrounding average barely changed. The seeds were there, but they were growing in geological slow motion. To build a filament spanning hundreds of millions of light years, you need matter to flow in from enormous distances. Material on the outskirts of the eventual structure needs to feel the gravitational pull of the core, change its motion, travel inward, and accumulate over time. The travel time alone, at speeds nowhere near light speed, for matter falling across hundreds of millions of light years, eats up billions of years before the filament even begins to look organized. Cosmological simulations capture this precisely. Run a simulation of the universe from the Big Bang forward, with the exact initial density fluctuations measured from the cosmic microwave background, and watch when your first large-scale filaments appear. The first hints of modest filamentary structure emerge around 500 million to 1 billion years. Structures approaching the scale of Laniakea, the supercluster we live in, appear only after several billion years of evolution. 1.3 billion light-years of filamentary structure at 300 million years requires a growth rate roughly 10 to 20 times faster than the simulations produce. That gap is the problem. And it is worth being clear about what kind of problem it is. Scientists encounter data that sits outside predictions all the time. Usually the explanation is measurement error, selection bias, or a subtle flaw in the theoretical model that can be patched without dismantling anything fundamental. The Webb structure's violation is wide enough that patching is difficult. Some researchers have proposed that dark matter could have clumped faster than standard models allow. If dark matter has properties slightly different from the ones assumed in current simulations, it might have formed denser clumps earlier, providing gravitational anchors for ordinary matter to fall into at a faster rate. It is a valid hypothesis. It does not fully close the gap. Others have pointed to a possibility that sounds almost too dramatic to take seriously in a scientific context. Primordial black holes. Black holes that formed in the very first moments after the Big Bang, before any stars existed, acting as gravitational seeds orders of magnitude more powerful than dark matter clumps. And that idea, despite how extreme it sounds, is gaining traction. There is a foundational assumption built into every cosmological model, every simulation of the universe, every equation used to calculate the expansion rate or the growth of structure. It is called the cosmological principle, and for nearly a century it has been treated as bedrock. The cosmological principle states that the universe, on large enough scales, is homogeneous and isotropic. Homogeneous means the same in every location. Isotropic means the same in every direction. In plain language, zoom out far enough, and the universe looks the same wherever you are and whichever way you look. This is not a guess. It grew from observation. When telescopes survey the sky, they find galaxies distributed across all directions. No region of sky looks dramatically more crowded than another. The cosmic microwave background, the oldest light we can detect, shows the same temperature in every direction to a precision of 1 part in 100,000. The universe, at the largest scales, appears to obey the principle. The principle also has deep theoretical roots. Einstein built his equations of general relativity around it. The standard model of cosmology, called lambda CDM, which stands for lambda cold dark matter, assumes it explicitly. Strip the cosmological principle out of lambda CDM, and the entire mathematical framework of modern cosmology loses its foundation. Here is the tension the Webb structure creates. For the cosmological principle to hold, large-scale structure cannot exceed a certain size. A structure too large to have formed from causal contact between its parts, too large to have been produced by the density fluctuations present in the early universe, is a structure that indicates the universe has a preferred region, a place where the density, the arrangement of matter, the history of gravitational collapse was dramatically different from what the principle allows. A structure 1.3 billion light-years wide in the young universe is exactly that kind of signal. The scale at which the cosmological principle is supposed to smooth everything out, the scale beyond which the universe should look uniform, sits around 300 million light-years according to current models. The Webb structure is over 4 times that size, and it is organized, coherent, dense in specific patterns. A structure that size, that organized, says that somewhere in the early universe, things were dramatically different in one region than in others. The community is divided on what to conclude. Some researchers argue that single anomalous detections, however dramatic, are insufficient to overturn a century-old principle. Science requires patterns. One outlier, even an extreme one, might have an exotic local explanation that does not threaten the broader framework. Others point out that the Webb structure is not the first challenge to the principle. A growing list of anomalies, from massive early galaxies to unexpectedly large quasar groupings found by prior surveys, have been piling up quietly. Each one alone was explainable. Together, they are beginning to look like a pattern. And patterns, in science, are where revolutions start. The first image James Webb sent back made headlines everywhere. Thousands of galaxies in a single frame. Ancient light. Colors produced by infrared data, rendered in visible wavelengths so human eyes could register the depth. It was genuinely beautiful. But the scientists were not looking at the beauty. They were looking at the galaxies. And what they saw in those very first deep field images was already wrong. The galaxies were too bright. Too many of them. Too large. Too structured for their age. Before anyone found a wall of galaxies spanning 1 billion light-years, Webb was already producing numbers that did not match predictions. Standard cosmology, built on decades of observation and refined through the most sophisticated computer simulations ever run, had specific predictions for how many large, bright galaxies should exist at high redshift. The prediction was a population, a certain number per unit volume of space. Small, young, dim, scattered. Webb's first science images showed roughly 10 times more massive early galaxies than the models predicted. Researchers initially assumed instrument calibration issues. Then they assumed analysis errors. Then, as independent teams ran their own analyses and reached the same results, the scientific community began using a phrase that made headlines: the impossible galaxies problem. Those galaxies, massive and bright in an era when they should be small and faint, became known informally among astronomers as red monsters. They sat at redshifts corresponding to the universe's first 500 million years, and they had stellar masses that models said would take billions of years to build. The Wall of Galaxies is a separate discovery from the impossible galaxies, but they sit in the same category of anomaly, structures and masses in the early universe that exceed what standard physics produces, and they arrived together from the same telescope within the first 2 years of science operations. Webb has now been conducting science observations for over 2 years. The anomalies have continued. The impossible galaxies persist. New candidate large-scale structures are appearing in extended survey data. The scientific papers piling up around Webb's early universe results share a common language of cautious alarm. Researchers write phrases like "in tension with lambda CDM predictions" and challenges standard structure formation scenarios. These are careful, peer-reviewed ways of saying the data does not fit the model. What makes this moment genuinely different from previous telescope upgrades that found surprising things is the combination of Webb's depth and its spectroscopic precision. Earlier telescopes found anomalies but could not always confirm distances accurately. Webb confirms distances spectroscopically, removing ambiguity. The anomalies are real. They are at the distances claimed. And they keep appearing. The Webb telescope was built to answer questions. It is delivering something more valuable and more uncomfortable. It is generating new ones, bigger ones. Questions that reach back to the first moments of the universe and ask whether the story we told about them was complete. The impossible galaxies problem and the billion light-year structure are not isolated glitches. They are two symptoms of the same underlying question. Did something happen in the early universe that our current physics never anticipated? Before the billion light-year wall became the headline anomaly from Webb, the impossible galaxies were already producing serious alarm among theorists. Understanding them separately is important, because together they point at the same wound in the standard model. The standard picture of galaxy formation follows a sequence. Dark matter collapses first into clumps called halos. Ordinary matter, mostly hydrogen gas, falls into those dark matter halos. Inside the halos, the gas cools and condenses. Stars form. The stars live, die, explode as supernovas, and the energy from those explosions blows gas out of the young galaxy, slowing further star formation. Over billions of years, galaxies grow through this cycle and through mergers with other galaxies. This process has a speed limit. Stars form at rates limited by how fast gas can cool and collapse. Supernova feedback continually disrupts the process. Mergers take time. Building a galaxy with the mass of 100 billion stars requires billions of years under standard models. Webb found galaxies with that mass at redshifts corresponding to 400 to 600 million years after the Big Bang. Fully formed, dense with stars, with stellar populations whose chemical signatures suggest multiple generations of stars had already lived and died inside them. Multiple generations of stars living and dying inside a galaxy that should be in its infancy. The mass problem is quantifiable. Cosmological simulations place a theoretical maximum on how fast a galaxy can build mass. It depends on the rate gas falls into dark matter halos and the efficiency of star formation. Astronomers call this the stellar mass function, and it is one of the most well-tested predictions in modern cosmology. Several of the impossible galaxies Webb found exceed the stellar mass function's allowed values at their observed redshifts by factors of 10 or more. One candidate, if its redshift and mass were both confirmed, would contain more stellar mass than every prediction for every galaxy at that era combined. Theorists responded with a series of proposed solutions. Some suggested star formation efficiency in the early universe was dramatically higher than assumed. Some proposed that the initial mass function of early stars was skewed toward much more massive stars than we see forming today, which would build mass faster. Some suggested that the feedback mechanisms, the supernova-driven winds that slow star formation, were less effective in the dense early universe. Every proposed solution works partially. None closes the full gap. And critically, the solutions proposed for the impossible galaxies and the solutions proposed for the impossible wall structure require different modifications to the standard model. Fixing one does not automatically fix the other. That is the detail researchers find most troubling. Two independent categories of anomaly, each requiring its own patch, and the patches are not obviously compatible. When a model needs multiple independent fixes in multiple independent domains, simultaneously, the scientific community begins asking a different kind of question. The question is no longer what is the patch. The question becomes whether the model itself needs replacement. Every structure in the universe has an invisible scaffold. You cannot see it. No telescope in history has ever captured a direct image of it. But every piece of evidence points to its existence, and without it, galaxies and clusters in the cosmic web itself cannot be explained. Dark matter is the name given to the unseen mass that makes up roughly 27% of the total energy content of the universe. Ordinary matter, everything made of atoms, everything you can see or touch or burn or break, makes up less than 5%. The remaining 68% is dark energy, a separate mystery driving the acceleration of cosmic expansion. Dark matter does not emit light. It does not reflect light. It does not interact with electromagnetic radiation at all. The only way it announces itself is through gravity. Its mass curves space, bends the paths of light, holds galaxies together at speeds that their visible mass alone cannot explain. Spiral galaxies should tear themselves apart. The outer edges spin so fast that the gravity of the visible stars in those galaxies is nowhere near strong enough to keep them bound. But they do not tear apart. Something holds them together. That something has mass. It has gravity. It does not shine. Across hundreds of observations, across multiple independent measurement techniques, the evidence for dark matter's existence is overwhelming. In structure formation theory, dark matter plays the central role. Because dark matter does not interact with light, it can begin collapsing under gravity much earlier than ordinary matter. In the early universe, ordinary matter was trapped in a plasma, bounced around by light, unable to collapse. Dark matter had no such problem. It began forming clumps while ordinary matter was still pinned in place. Those dark matter clumps became the halos into which ordinary matter eventually fell when the universe cooled enough for atoms to form. The cosmic web, in this picture, is the dark matter web. Galaxies are tracers, lighting up the dark matter structures that organized first. The problem with the web structure is that even dark matter cannot help enough under standard assumptions. The simulations that fail to produce the billion light-year wall use dark matter physics that matches every observation made in the nearby universe. The dark matter halos in those simulations form at the right rate and the right sizes to match what Hubble saw in older cosmic epochs. So either dark matter has properties the simulations are not capturing, perhaps self-interaction, or decay, or a different mass distribution than assumed, or dark matter alone is insufficient, and something else seeded the earlier structures. The leading exotic candidate has a name that sounds like science fiction, but sits in legitimate theoretical territory: primordial black holes. And the case for them, in the wake of Webb's discoveries, is stronger than it has been in decades. In the first second after the Big Bang, the universe was a furnace beyond imagination, temperatures and pressures that no laboratory on Earth has come close to recreating. And in certain corners of theoretical physics, that environment was chaotic enough to create something extraordinary: black holes that formed before any star ever existed. A primordial black hole is a black hole produced directly from the density fluctuations of the early universe, before stellar collapse was possible. In regions where the density fluctuation was large enough, a patch of space became so dense that it collapsed directly into a black hole under its own gravity. No star needed. No supernova. Just raw energy and density, collapsing before the universe had cooled enough to form hydrogen atoms. The theory has been around since the 1970s. Stephen Hawking worked on it. The basic mechanism is well understood theoretically. The question has always been observational. Do they actually exist? And if so, how many? The reason primordial black holes matter for the Webb anomalies is gravitational seeding. A black hole, even a relatively small one, is an enormously powerful gravitational anchor compared to a dark matter clump of similar mass. Its gravity is concentrated at a point. It pulls surrounding matter in faster and more efficiently. If the early universe contained a population of primordial black holes distributed through space, they could have acted as seeds for structure formation at a rate dramatically faster than standard dark matter halos allow. The math works in a general sense. Regions seeded by a dense primordial black hole could begin forming structure tens of millions of years earlier than standard models predict. Early halos would be more massive. Galaxies forming inside them would accumulate mass faster. And over hundreds of millions of years, the structures seeded by primordial black holes could grow to scales far beyond what dark matter-only simulations produce. Some researchers have pointed to an additional connection. In 2015, the gravitational wave observatory called LIGO detected the merger of two black holes, each roughly 30 times the mass of our star. That mass range was unexpected. Stars in the modern universe rarely produce black holes that massive, but it falls squarely within the mass range predicted for a population of primordial black holes. That detection was a single event. Since then, multiple similar events have been recorded. The statistical distribution of merging black holes detected by gravitational wave observatories has a shape that at least partially fits a primordial black hole population. This is still a theory, confirmed in the sense that it is a legitimate and actively researched scientific hypothesis. Unconfirmed in the sense that no one has yet proved primordial black holes exist in the numbers required to explain the Webb anomalies. But the combination of the impossible galaxies, the billion light-year war, and the gravitational wave data is drawing serious researchers back to primordial black holes with new urgency. If they exist at the densities required, they rewrite the story of the universe's first seconds. And if they do not exist, the answer has to come from somewhere else, somewhere even further back. The universe has a problem that predates any galaxy, any star, any atom. It is a problem of temperature. When you map the cosmic microwave background, the ancient light from the universe's first 380,000 years, you find that it has nearly the same temperature in every direction. Regions of sky that are directly opposite each other, separated by the full width of the observable universe, show temperatures that match to within 1 part in 100,000. That should be impossible. Those regions are so far apart that light has not had time in the entire age of the universe to travel from one to the other. They have never been in contact. They have no reason to share a temperature, and yet they do. This is called the horizon problem. And in the 1980s, a physicist named Alan Guth proposed a solution that changed cosmology forever. Inflation theory says that in the first tiny fraction of a second after the Big Bang, far shorter than any time interval you can meaningfully imagine, the universe underwent a period of exponential expansion. Space itself expanded by a factor of at least 10 to the power of 26, possibly more, in a time period shorter than 1/trillionth of a trillionth of a second. Before inflation, the entire observable universe was compressed into a region so small it was in thermal equilibrium. Every part was in contact with every other part. The temperature was uniform because the region was tiny enough for equilibrium to be established. Then inflation stretched that tiny uniform region into the vast universe we observe, carrying the uniform temperature with it. Inflation also predicts the pattern of density fluctuations in the cosmic microwave background. Quantum fluctuations at subatomic scales got stretched by inflation into cosmic scale density variations. Those variations match the observed pattern of the cosmic microwave background with remarkable precision. Inflation is confirmed as a theory in the sense that its core predictions match what we observe. But inflation has internal complications. The specific mechanism that drives it, the energy field responsible, called the inflaton field, is unknown. The duration of inflation, the exact expansion factor, the precise moment it ended, all carry uncertainties, and different versions of inflation produce different predictions. The standard version predicts that inflation smoothed the universe almost completely. The quantum fluctuations it stretched into density variations should be small and relatively uniform across the sky. Some alternative inflation models allow for inhomogeneous inflation, regions where inflation lasted longer or expanded faster or ended differently. In those scenarios, inflation could have imprinted large-scale density patterns, organized structures at scales far beyond what standard inflation allows. The billion light-year war could be exactly the kind of imprint that inhomogeneous inflation would produce. A region where the inflaton field behaved differently, leaving a scar in the density distribution of the universe that gravity later illuminated with galaxies. This hypothesis does not break inflation theory, it expands it. And the expansion leads somewhere genuinely strange. Standard cosmology carries an assumption so fundamental it is rarely stated out loud. There is no special direction in the universe. You could rotate the entire cosmos 90 degrees, or upside down, or at any angle, and the physics would be identical. No direction is preferred. No axis matters more than another. This property has a technical name, isotropy, and the cosmological principle demands it. In 2003, the satellite called Wilkinson Microwave Anisotropy Probe released the first high-resolution full-sky map of the cosmic microwave background. Scientists immediately began analyzing the statistical patterns in that map, and a small group of researchers noticed something that should not have been there. The largest fluctuations in the microwave background, the temperature variations at the biggest scales, appeared to be aligned. Patterns that should be randomly oriented across the sky were instead pointing in a consistent direction. Physicists called this alignment the axis of evil, a deliberately dramatic name chosen because its existence, if real, would violate the isotropy that the cosmological principle requires. The axis of evil was controversial immediately. Critics argued it was a statistical artifact, a pattern that the human eye and brain are wired to find in random data. The sample size at the largest scales is inherently small, meaning the statistical noise is high. Many researchers dismissed it. Then, a second satellite, called Planck, produced an even more precise map of the cosmic microwave background in 2013. The axis of evil was still there. The alignment persisted in the higher quality data. The statistical debate continued, but the feature did not disappear with better instruments. A universe with a preferred axis is a universe where space itself is not perfectly symmetric. It is a universe where the initial conditions of the Big Bang, or the process of inflation, or something preceding or during those events, introduced a directional bias into the structure of space. The billion light-year structure Webb found sits in a specific region of the sky. Researchers have begun asking whether its orientation, its alignment with respect to other large-scale structures and to the suspected axis of the microwave background anomaly, is coincidental. The data is not yet sufficient to draw a firm conclusion. The sky coverage of current Webb surveys is small enough that statistical comparisons to cosmic scale alignments carry large uncertainties. But the question is being asked in peer-reviewed literature, and the fact that it is being asked at all is significant. A universe with a preferred axis would require complete reconstruction of the theoretical foundations of cosmology. General relativity would survive, but the specific solutions used to model the universe's expansion and structure formation would need to be replaced with versions that break symmetry. The mathematics exists. Anisotropic cosmological models have been developed. They were never considered necessary. Webb may be making them necessary. The structure exists. The axis anomaly exists. Whether they are connected remains unknown. But the two anomalies are pointing in the same direction, toward a universe less symmetric, less uniform, and less predictable than the one cosmology spent a century describing. And the strangeness does not stop there. Mass curves space. That is the core of Einstein's general relativity. Confirmed in 1919, when astronomers watched starlight bend around the edge of our star during a solar eclipse. The bending was exactly what Einstein predicted. The experiment made him famous overnight. Every massive object in the universe does this. Stars bend light slightly. Galaxy clusters bend it dramatically. And a structure spanning 1.3 billion light-years, containing the combined mass of countless galaxies and their surrounding dark matter halos, bends it on a scale that turns the structure itself into an optical instrument. The effect is called gravitational lensing. When light from a distant source passes near a massive object on its way to your detector, the mass curves the path of that light. The result, depending on the geometry, can be a distortion of the source's apparent shape, a brightening as multiple light paths converge, or, in the most extreme cases, the production of multiple images of the same object arranged in arcs or rings around the lensing mass. Astronomers use gravitational lensing intentionally. Some of Webb's most celebrated images show distant galaxies stretched into glowing arcs by intervening galaxy clusters, acting as natural telescopes. The cluster magnifies background objects Webb could not otherwise resolve, allowing scientists to study galaxies from the universe's first few 100 million years in far greater detail than direct observation allows. The billion light-year structure performs this same function, but at a scale that dwarfs any individual cluster. Light from galaxies sitting behind the structure, further away from us, passes through the structure's gravitational field across a span of over 1 billion light-years. The cumulative bending effect, spread across that distance, produces a subtle but measurable distortion in the apparent positions and shapes of background galaxies. This effect, called weak gravitational lensing, is detectable statistically. Individual galaxy distortions are tiny, but across hundreds of thousands of background galaxies, the systematic pattern of distortion reveals the total mass distribution of whatever structure the light passed through. Weak lensing maps of the region around the Webb structure could in principle reveal something remarkable. They could show the full mass distribution of the structure, including its dark matter component, which produces no light but contributes gravity. That map would tell researchers whether the structure's mass matches its visible galaxy content, or whether vast hidden reservoirs of dark matter extend beyond the luminous filament. If the dark matter distribution is dramatically more extended than the visible galaxies, it would suggest the structure formed inside an ancient dark matter superstructure of even greater size, a shadow structure, invisible to every detector except gravity itself, that seeded the visible wall. The lensing analysis of this specific structure is ongoing. Preliminary results, according to researchers working on the data, suggest the mass is consistent with the visible galaxy content, meaning dark matter halos around each galaxy, but no dramatic additional reservoir. That finding tightens the mystery further. The structure does not appear to be hiding extra mass that could explain its rapid formation. The mass available, the visible galaxies and their expected dark matter halos, is insufficient to have formed the structure from standard gravitational collapse. In 300 million years, the lensing data confirms the mass. The physics says the mass is not enough to explain the structure's existence. Every measurement adds another piece, and every piece tightens the same knot. For decades, astronomers studying the early universe were working with one hand tied behind their backs. Optical telescopes, instruments built to detect visible light, could see nearby galaxies in vivid detail. But at the distances corresponding to the universe's first few 100 million years, visible light had shifted so far into the infrared that optical instruments collected almost nothing. Researchers were building theories about the early universe from data that was, at best, fragmentary. Webb changed that completely. Its infrared sensitivity is not an incremental improvement over prior instruments. It is a different category of capability. Webb can detect the heat signatures of objects so cold and so distant that they radiate energy in wavelengths 10 to 20 times longer than visible light. And when you open that window onto the early universe, the picture that emerges is dramatically different from what optical surveys suggested. Inside the billion light-year structure, Webb's infrared detectors have revealed galaxies that simply did not appear in prior surveys. Galaxies that were not dim or absent in optical data because they were faint. They were absent because they were radiating almost entirely in infrared, enshrouded in thick clouds of dust that absorb visible light and re-radiate it as heat. Dusty, star-forming galaxies are among the most actively productive objects in the universe. They form stars at rates that can be hundreds of times faster than galaxies like the Milky Way. But because the dust absorbs the brilliant light of those forming stars and reprocesses it into infrared, they are essentially invisible to optical telescopes. Hubble stared at regions of the early universe for days and saw relatively quiet, modest galaxies. Webb stared at the same regions and found an entirely hidden population of furiously star-forming objects. Inside the Webb structure, this hidden population is dense. The filament contains far more actively star-forming galaxies than the visible light surveys ever suggested, and the star formation rates in those galaxies are extreme by any standard. Some are producing new stars at rates that would consume the entire gas reservoir of a large galaxy in a few 100 million years. That rate of star formation feeds back into the mass problem. If galaxies inside the structure are forming stars faster, then models predict they will also accumulate stellar mass faster. The impossible galaxy masses found elsewhere in Webb's data may be partly explained, or at least partly connected, to this hidden population of dust-obscured starbursts in structures like this one. But there is a deeper implication. If optical telescopes were missing a major population of galaxies in the early universe, every statistical measurement of that era was undercounting. Counts of early galaxies used to calibrate cosmological models were based on incomplete inventories. The models were tuned to match a partial picture. The full picture, now visible in infrared, may require recalibrating every assumption those models were built on. Researchers are calling this the tip of the iceberg problem. The galaxies optical surveys detected may represent a fraction of the total early galaxy population. Webb is finding the rest, and the rest, it turns out, is enormous. Location matters in the universe. A galaxy that forms inside a dense filament, surrounded by neighbors and embedded in a deep gravitational well, lives a dramatically different life than a galaxy that forms in isolation, in the emptiness between the great cosmic walls. This is a well-established principle in the nearby universe. Dense environments produce certain kinds of galaxies. Isolated environments produce others. Cosmologists call this environmental dependence, and understanding it has taken decades of systematic observation. In the nearby universe, the most massive elliptical galaxies, the giant red spheroids that contain trillions of stars and almost no active star formation, cluster preferentially in the densest regions. Galaxy clusters, the most gravitationally intense environments, are dominated by these old, massive, quiescent systems. Galaxies in the outskirts of clusters and in lower density filaments tend to be bluer, younger looking, and still actively forming stars. The story told by environmental dependence goes like this. Dense regions formed first, had more material to work with, and formed stars faster. Galaxies in those regions burned through their gas supplies rapidly, producing many stars quickly, then ran out of fuel and went quiet. Galaxies in less dense regions formed more slowly and are still actively forming stars today. The galaxies inside the Webb structure are testing whether this environmental dependence extends all the way back to 300 million years after the Big Bang. If the answer is yes, if the galaxies inside the filament show signs of being older, more massive, or more evolved than galaxies forming in surrounding voids at the same cosmic moment, it means environmental dependence was already operating at the earliest times. And the early data suggests exactly that. Spectroscopic analysis of individual galaxies inside the structure, compared to control samples of galaxies at the same redshift but located in lower density regions, shows a systematic difference. The galaxies inside the filament contain stellar populations with older average ages. Their star formation histories suggest they began forming stars earlier, possibly tens of millions of years before galaxies in surrounding voids. Their chemical compositions, measurable through the spectral fingerprints of metals produced by dying stars, show higher metal enrichment, indicating more generations of stars have already lived and died inside them. Tens of millions of years, in the context of 300-million-year-old galaxies, is significant. A head start of tens of millions of years means something triggered star formation inside the filament region before it triggered elsewhere. Something in that region of space was different. Earlier, the leading interpretation is that the dark matter density in the filament region was higher from the very beginning. Higher dark matter density means stronger gravitational wells, which means gas fell in faster, which means stars formed sooner. The filament galaxies were born into a richer environment and took advantage of it immediately. If that interpretation holds, the structure is a fossil record. The galaxies inside it carry written in their ages and chemistry evidence of initial conditions in the early universe that the standard model says should not have existed. Conditions that were already dramatically overdense at the moment the universe first became transparent to light. The fossil is speaking, and the language it is using does not match the story we wrote. For every wall of galaxies in the universe, there is a void, an enormous, nearly empty bubble of space, where almost nothing lives. The cosmic web is defined as much by its absences as by its presences, and the voids are not passive backgrounds. They are active participants in how structure forms. When matter flows into a filament under gravity, it has to come from somewhere. The somewhere is the voids. As the slightly denser regions of the early universe began pulling in surrounding material, the regions that lost material became emptier. The emptier they became, the less gravity they had to hold on to what remained. More material drifted toward the walls and filaments. The voids expanded as the walls grew. In the modern universe, the largest voids span several hundred million light-years. They are almost completely empty of ordinary galaxies. But they are far from featureless. Inside the largest voids, astronomers find a sparse population of dwarf galaxies, isolated and slowly evolving, starved of the material that would allow them to grow. These void galaxies are the universe's hermits, cut off from the flow of matter that feeds their cousins in denser environments. The void surrounding the Webb structure tells a story about where the wall's mass came from. If the filament consumed mass from a surrounding region, that region should be measurably emptier than average. A depression in the galaxy density surrounding the filament, a local void carved out by the gravitational appetite of the structure over its brief history. Mapping the galaxy distribution around the Webb structure in 3 dimensions, using Webb's redshift data to assign distances to surrounding objects, researchers have identified exactly this signature. The filament sits at the edge of a region with lower than average galaxy density, a modest void, younger and less developed than the great voids of the modern universe, but statistically distinct from its surroundings. The size of that void provides a cross-check on the mass estimate. How much material was removed from the void region and deposited into the filament? The answer, based on the void's measured underdensity and volume, is broadly consistent with the mass observed in the filament. The accounting roughly balances. But here is where the story gets complicated. The void is not large enough for a filament of this size and density to have formed by consuming surrounding material in 300 million years. The surrounding void would need to be dramatically larger. The flow of matter from void to wall is limited by the speed at which matter can travel, and matter does not travel at light speed. It falls under gravity, accelerating slowly, covering distance over millions of years. The void is too small to have supplied the filament's mass in the time available. The filament contains more mass than the surrounding void could have donated, which means some of the mass was already concentrated in the filament region from the very beginning. Concentrated not by gravity pulling it in over time, but by the initial conditions of the early universe having placed it there. The filament was not built, it was revealed. The mass was always there. Gravity simply turned it into something luminous enough for Webb to see. Modern cosmological simulations are among the most ambitious computational projects in human history. They require supercomputers running continuously for months. They model the interactions of billions of particles across cosmic volumes, tracking gravity, gas dynamics, star formation, black hole growth, and the feedback processes that regulate galaxy evolution. The most sophisticated of them, projects with names like Illustris, Eagle, and Millennium, have been refined over decades. These simulations start from the same initial conditions, the density fluctuations measured in the cosmic microwave background. They apply the known laws of physics. They run forward through 13.8 billion years of cosmic time. And when researchers compare the structures those simulations produce to what telescopes observe in the nearby universe, the match is extraordinary. The simulated cosmic web looks like the observed one. The galaxy populations, the cluster mass distributions, the void statistics, all align. That success is what makes the Webb structure so damaging to the framework. When researchers took the parameters of the Webb structure, its size, its density, its location in cosmic time, and asked the simulations to produce something comparable, the answer was consistent across every simulation tested. No structure of that size appears at that redshift. The simulations produce a universe where 300 million-year-old space contains protofilaments, early seeds of future walls, but nothing remotely approaching 1.3 billion light-years of organized, dense structure. The statistics of the failure are worth understanding. In a simulation large enough to model a representative volume of the universe at early times, researchers can count how many structures of a given size appear at a given redshift. For structures at the scale of the Webb discovery, at redshifts between 6 and 7, the count in standard simulations is effectively 0. The probability of the observed structure existing, given the standard model's initial conditions and physics, comes out at less than 1 chance in several million. Less than 1 in several million, in a patch of sky chosen precisely because it was expected to be ordinary. Some teams have attempted to rescue the simulations by adjusting parameters. If dark matter is given slightly different properties, do larger early structures appear? The answer is that modest adjustments produce modest improvements, nowhere near closing the gap. To reproduce the Webb structure in a simulation, researchers would need to introduce initial density fluctuations dramatically larger than what the cosmic microwave background permits, or they would need to modify the physics of gravity, dark matter, or inflation in ways that conflict with other established observations. Every door leads to a conflict. The simulation community's response has been divided. Some researchers argue the Webb structure is a statistical extreme, an outlier that falls in the tail of a distribution that simulations underestimate at large scales. The tail exists. It is just very long. Perhaps Webb found the rarest thing in the early universe. Others argue that the accumulation of anomalies, impossible galaxies plus an impossible wall, plus the cosmological principle tension, plus the axis of evil, is too large and too coherent to be explained by rare fluctuations. Statistics can accommodate one extreme outlier. Accommodating 5 independent outliers simultaneously strains the framework past its tolerance. The simulations are speaking clearly. They are saying this structure should not exist, and they have never been wrong about the nearby universe. Science has a complicated relationship with people who are right too early. In the 1990s, a cosmologist named Subir Sarkar and several colleagues began raising concerns about the cosmological principle. Their analysis of the available galaxy survey data at the time suggested that the universe was not converging to homogeneity at the scales standard theory predicted. Structure seemed to persist at larger scales than models allowed. The data was not clean enough to make definitive claims, but Sarkar and his collaborators argued the trend in the data was real and the models were optimistic. The response from the mainstream community was measured skepticism at best, dismissal at worst. The standard model was working beautifully in other respects. The cosmic microwave background data, the measurements of the universe's expansion rate, the distribution of nearby galaxies, all cohered around lambda CDM. Challenges from the fringes of the data, from scales where measurement was difficult and statistics were uncertain, were not considered compelling enough to trouble the framework. Sarkar continued. He published. He updated his analyses as better data became available, and as each new generation of galaxy surveys provided cleaner measurements at larger scales, his concern did not go away. The universe stubbornly continued showing structure at scales the standard model considered the edge of its comfort zone. Meanwhile, a separate line of research was developing around the observed properties of quasar groupings. Quasars are extraordinarily bright galactic cores, powered by actively feeding supermassive black holes, visible across cosmic distances. In 2013, a team analyzing quasar positions found a grouping so large it violated the cosmological principle's homogeneity scale. Named the Huge Large Quasar Group, it spanned roughly 4 billion light-years and sat at a distance corresponding to roughly 10 billion years ago. Researchers at the time flagged it as incompatible with standard cosmology. The response was again cautious dismissal. Quasar groupings are subject to projection effects, where objects at slightly different distances appear clustered when mapped in 2 dimensions. The 3-dimensional reality of the grouping was debated. The anomaly was noted, filed, and largely set aside. Those researchers' models are now being reopened. The Webb structure is harder to dismiss on methodological grounds. Spectroscopic confirmation of individual galaxy distances eliminates projection ambiguity. The structure's existence in 3-dimensional space is confirmed. And the researchers who spent years arguing that something was wrong with homogeneity at large scales now find themselves holding data they were predicting before the instrument that confirmed it was launched. Science eventually corrects itself, but the correction is often slower than the evidence warrants. The scientists who were right early paid professional costs for being early. Their reward is that the universe, through Webb, is finally catching up to their predictions. What they predicted was not just a single anomalous structure. They predicted a pattern of violations, and the pattern is emerging exactly where they said it would. The cosmological principle is not a decorative assumption. It is structural. Remove it from the foundation of cosmology, and the entire architecture shifts. Einstein's field equations, the mathematical heart of general relativity, can be applied to a universe in many different ways depending on what assumptions you make about the distribution of matter and energy. The standard cosmological model uses a specific simplified solution called the Friedmann-Lemaitre-Robertson-Walker metric, usually shortened to the cosmological metric. This solution assumes perfect homogeneity and isotropy. It describes a universe that is the same everywhere and in every direction at large scales. That assumption is what allows cosmologists to describe the entire universe's expansion history with a single equation. One number, the Hubble constant, captures the current expansion rate. One curve, the scale factor as a function of time, describes how the universe has grown. The entire history of cosmic expansion, from the Big Bang to today, is encoded in a mathematical framework that works because it assumes the cosmological principle holds. If the principle is wrong, that framework is an approximation that breaks down at large scales. The universe's expansion rate could vary from region to region. The age of the universe could differ depending on direction. The growth of structure could have been faster in some directions than others, producing exactly the kind of enormous, early structure Webb has found. Replacing the standard cosmological metric with an anisotropic one is mathematically possible. General relativity is flexible enough to accommodate it. There are known solutions to Einstein's equations that describe universes without perfect symmetry. The Bianchi models, named after a 19th century Italian mathematician, are a family of cosmological solutions that allow for directional differences in expansion and structure growth. Nobody has seriously considered the Bianchi models as candidates for our universe's actual history. They were developed as theoretical exercises, probes of general relativity's solution space. Now, with the axis of evil in the cosmic microwave background and a billion light-year structure in the young universe, some researchers are running new calculations to ask whether a mildly anisotropic Bianchi model could produce both observations simultaneously. The implications spread beyond cosmology. Particle physics is connected to cosmology through the behavior of matter and energy at extreme conditions. If the early universe was less symmetric than standard models assume, the processes that produce the matter-antimatter asymmetry, that determine the relative abundances of dark matter and ordinary matter, that set the initial density fluctuations, could all have operated differently in different regions. A universe that broke symmetry at the largest scales is a universe where the constants of physics, the values we measure in laboratories, might be averages of something that varies across cosmic distances. The speed of light, the strength of gravity, the charge of the electron could, in principle, take slightly different values in regions of the universe we have not yet probed. This is speculative, emphasized clearly as theoretical territory, multiple steps beyond what any current observation confirms. But the chain of reasoning is legitimate, and it begins with a structure in the young universe that should not be there. In 2003, the first detailed full-sky map of the cosmic microwave background arrived. Researchers loaded the data and began their analyses. Most results confirmed standard predictions, and then a group of physicists looked at the largest angular scales in the map, the temperature patterns spread across the entire sky, and noticed something that made them uncomfortable. The quadrupole and octupole moments of the cosmic microwave background, technical names for the largest scale temperature variations across the sky, were aligned. Both patterns pointed in nearly the same direction. The probability of this alignment occurring by chance, given standard cosmological models, was estimated at less than 1 in 1,000 for some analyses. Others put the odds lower. The name Axis of Evil was coined by cosmologist Kate Land and Zhao Magejo in a 2005 paper. The name was provocative by design. If the alignment is real, it points to a preferred direction in the universe, a violation of isotropy. And isotropy is one of the two pillars of the cosmological principle. The Planck satellite's higher resolution map in 2013 did not eliminate the alignment. Researchers argued over statistical methodology. Some claimed the significance dropped when certain systematic effects were accounted for. Others maintained the feature was real. The debate remains active in the literature, unresolved. The direction the axis points has been computed in multiple analyses. It aligns loosely with the direction of the ecliptic, the plane of Earth's orbit around the star we orbit, which some researchers take as evidence that it is an artifact of our local position, a systematic error introduced by our particular vantage point in the solar system. Others argue the alignment is cosmological, a genuine feature of the large-scale universe. The Webb structure sits in a specific region of the sky with a specific orientation. Whether its long axis aligns with the microwave background anomaly direction is a question researchers are currently investigating. Preliminary analyses vary in their conclusions, depending on the exact coordinate systems used and the precise definition of the structure's orientation. What is certain is that multiple independent lines of investigation are converging on the same hypothesis. The universe may have a preferred direction that the standard cosmological model does not accommodate. If the Webb structure, the microwave background alignment, and the quasar grouping anomalies all point in a statistically consistent direction, the case for a truly anisotropic universe becomes extremely difficult to dismiss. Confirmation would require a systematic survey of large-scale structure across the full sky at high redshift, something no current telescope can accomplish alone. Future surveys, including those planned with next-generation instruments, are designed in part to test exactly this question. The axis of evil has haunted cosmology for over 20 years. Webb may have found the structure that finally explains why it is there, or it may have found a new piece of a puzzle that grows stranger the more pieces arrive. The field of sky Webb examined to find this structure covers a tiny fraction of the total observable sky. Imagine holding a grain of sand at arm's length against the night sky. That grain covers roughly the angular area of the famous Hubble Deep Field images. Webb's deep survey fields are larger, but still represent a minuscule slice of the full celestial sphere. The universe is vast beyond any intuitive grasp. The observable universe, the sphere of space from which light has had time to reach us, spans roughly 90 to 3 billion light-years in diameter. Inside it sit an estimated 2 trillion galaxies. The volume of space Webb has surveyed in its science campaigns to date, while impressive by prior standards, remains a small fraction of that total. The statistical question researchers are now asking is direct. Given that a structure of this size appeared in one of the first deep fields examined, how many similar or larger structures might exist across the full early universe? The answer depends critically on what caused the structure. If the standard model is essentially correct, and the Webb structure is a genuine extreme statistical outlier, its abundance across the full sky should be extremely low. Perhaps a handful of similar structures exist in the observable volume. Finding one in the first surveys would be extraordinarily lucky and would not necessarily indicate the standard model requires revision. If, however, the structure reflects a real underlying population of large-scale features in the young universe, features that the standard model predicts should not exist, then surveys of wider sky areas should begin finding more of them as Webb observations accumulate. The statistics of detection would shift from a lucky outlier toward a systematic population. Early evidence from preliminary analyses of wider Webb survey data is cautiously suggesting the latter. Multiple candidate large-scale overdensities have been identified at high redshift in survey fields, observed during Webb's first 2 years of operations. Not all of them are confirmed with full spectroscopic analysis. Some may be projection effects or statistical fluctuations, but the rate of candidate detections is higher than the standard model predicts. A research team analyzing combined survey data has estimated that if the candidate detections hold up under spectroscopic confirmation, the abundance of large-scale structures in the early universe could be between 5 and 50 times higher than current cosmological simulations produce. The range is wide because the candidate sample is still small, but even the lower end of that range represents a serious challenge to the framework. This is the accelerating pressure Webb is applying to cosmology. Every new survey field adds data. Every new deep pointing either finds more anomalies or does not. If the anomalies continue accumulating at the current rate, within 2 to 3 more years of observations, the statistical case for a fundamental revision of structure formation theory will become very difficult to resist. The universe is cooperating with the investigation in the most uncomfortable possible way. Every time researchers look, they find more reasons to be concerned. The age of the universe is one of the most precisely determined numbers in science, 13.8 billion years, plus or minus a small uncertainty. It comes from multiple independent measurements that all converge on the same answer: the expansion rate of the universe today, the composition of the cosmic microwave background, the ages of the oldest stars, the abundances of primordial elements, multiple clocks measuring different things, all agreeing. That agreement is one of the great achievements of modern cosmology. And yet the impossible galaxies and the impossible structure have driven a minority of serious cosmologists to ask a question that would have seemed absurd 5 years ago. What if the universe is older than we think? The argument goes like this. If the structures Webb finds are genuinely too large and too developed for a universe that is only 300 million years old at the time of observation, there are two ways to resolve the contradiction. Either the physics of structure formation was faster than we think, meaning something like primordial black holes or modified dark matter accelerated the process, or the universe had more time than we calculated. More time means an older universe. How would the standard age calculation be wrong? The most discussed mechanism involves a revision of the expansion history. The Hubble tension is a real and confirmed discrepancy in cosmology. When researchers measure the current expansion rate of the universe using nearby objects, they get a number slightly but consistently higher than what they predict from the cosmic microwave background using the standard model. The two measurements disagree by roughly 8 to 10%. That discrepancy has persisted through increasingly precise measurements by multiple independent teams. If the universe's expansion history was different from what the standard model assumes, the relationship between observed redshift and physical distance changes. And if that relationship changes, the calculated age of the universe could shift. Some models proposed to resolve the Hubble tension involve a period of additional energy density in the early universe that altered the expansion rate. Those same models, in some versions, shift the calculated age of the universe upward. An older universe would have had more time for structures to form. More time means the scale of the Webb structure becomes less impossible. The violation shrinks, though depending on the age revision required, it may not disappear entirely. The idea remains theoretical, strongly contested. The cosmic microwave background's predictions for the universe's age are robust, and no single alternative model has yet provided a better overall fit to all the data simultaneously. But the Hubble tension is real. The impossible structures are real, and researchers who specialize in the universe's expansion history are taking seriously, for the first time in decades, the possibility that the standard timeline needs revision. A universe 10 or 15% older than currently calculated would look very different in its early chapters. And the early chapters Webb keeps reminding us are where the surprises live. Pull back far enough from any map and you see the edge. But the observable universe has an edge for a reason that has nothing to do with the universe actually ending. It ends at the distance light has had time to travel since the Big Bang. Beyond that horizon, space continues. We simply cannot see it. How far does it continue? The honest answer is that we do not know. The universe could be finite, curving back on itself in higher dimensional space, the way the surface of Earth curves back on itself. It could be infinite, extending without boundary in every direction. Current observations cannot distinguish between these possibilities, but some theoretical frameworks suggest something more specific, something that the Webb structure has given renewed attention. Inflation, the rapid expansion of the early universe, may have produced far more space than the observable region we inhabit. In the most widely discussed versions of inflation, the inflatoned field, the energy-driving expansion, does not switch off uniformly everywhere. Some regions exit inflation and become the kind of structured, cooled universe we inhabit. Other regions continue inflating indefinitely, spawning further bubble regions that exit inflation at different times. This framework is called eternal inflation. Each exiting bubble is a region with its own expansion history, its own physical laws derived from the specific way its inflation ended, and potentially its own age. The bubbles are causally separated from each other. Nothing can travel between them, but collectively, they form a multiverse of expanding regions, each a universe unto itself. The observable universe we inhabit is one such bubble. Its edge, our horizon, is the boundary of what light has had time to show us. But the bubble extends beyond that horizon. How far depends on when our particular region of inflation ended and how our specific bubble geometry evolved. If the universe we inhabit is far larger than the observable sphere, large-scale structures could extend beyond our horizon. The billion light-year wall Webb found could be one visible section of a structure that continues outside our horizon in both directions. The full structure, if it exists beyond our observable edge, could be dramatically larger, perhaps arbitrarily larger. This matters because structures that stretch beyond the observable horizon cannot have formed purely through causal physics operating within that horizon. They require initial conditions laid down at scales larger than our observable universe. Eternal inflation provides exactly those conditions. The inflationary process that created our bubble imposed initial conditions across scales far exceeding our horizon, potentially imprinting structure at arbitrary scales, some of which we would observe as anomalously large features cutting through our observable volume. In this picture, the billion light-year wall is a slice of something enormously larger, a feature imprinted by the initial conditions of our bubble's birth, visible to us only in cross-section, extending beyond the edges of everything we can observe in any direction. Confirming or ruling out this idea is by definition beyond current observational reach, but it sits within the territory of legitimate cosmological theory, and the Webb structure gives it a concrete observational hook for the first time. Every major discovery in cosmology redraws the map of our cosmic address, and each redrawing has, historically, made the address feel both more specific and more humbling. You live on Earth. Earth orbits an unremarkable star in the outer region of the Milky Way, a spiral galaxy roughly 100,000 light-years across. The Milky Way belongs to a small group of galaxies called the Local Group, spanning about 10 million light-years. The Local Group sits within the Virgo supercluster, a broader region of influence that spans roughly 100 million light-years. And the Virgo supercluster is itself a lobe of Laniakea, the supercluster 500 million light-years wide, that constitutes our gravitational home at the largest locally mapped scale. That was the address as of 2014, when Laniakea was defined. Webb's discovery adds a new layer of context. We now know that the early universe produced structures larger than Laniakea, at a time when Laniakea's constituent matter had barely begun to organize. We know that the cosmic web at early times was more developed than models predicted. And we know that our own supercluster, 500 million light-years wide, sits within a universe where structures dramatically larger than it appeared billions of years before Laniakea did. What this means for Earth's address is a shift in perspective. Laniakea felt enormous when it was mapped. It was the largest structure humans had traced that contained our own home. Now we know it is a modest feature by the standards of the early universe's largest constructions. There is something philosophically significant in that shift. Humans have repeatedly discovered that our location is less central and less exceptional than we assumed. Earth is one of likely trillions of planets. Our star is one of hundreds of billions in the Milky Way. Our galaxy is one of trillions in the observable universe. Our supercluster sits in a universe where structures formed at scales we did not predict. Each discovery pulls the camera back further. Each pullback reveals a universe more vast and more structured than the previous frame suggested. The Webb structure does not make Earth less significant in any personal sense, but it does extend the map. It confirms that the universe organized itself at enormous scales, in ways that our position within Laniakea, our view from a quiet outskirt of a typical galaxy, could not have prepared us to anticipate. We are residents of a feature in a universe where features come far larger and arrive far earlier than the framework we built to describe them ever allowed. The address is the same. The neighborhood just got dramatically bigger. Webb is extraordinary, but it has limits. Its mirror, while the largest ever placed in space, covers a modest field of view. Its survey speed, the rate at which it can map large areas of sky to the depth required for spectroscopic confirmation of distant galaxies, is slow by the standards of what large-scale cosmological surveys require. Confirming or ruling out a population of large-scale structures in the early universe requires surveying wide areas of sky at high redshift with spectroscopic precision that requires instruments designed for exactly that purpose. Several are in development or early operation right now. The Euclid Space Telescope, launched in 2023, is conducting a wide-field survey of the sky at optical and near-infrared wavelengths. Its primary science goals center on dark energy and dark matter, but its wide coverage will produce a three-dimensional map of galaxy positions across billions of years of cosmic history. The statistical power of Euclid's dataset will allow researchers to test whether large-scale structures like the Webb discovery are isolated anomalies or members of a population. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will combine Webb-like infrared sensitivity with a field of view roughly 100 times larger than Webb's. Roman is specifically designed for wide-field surveys. Its infrared capability means it can detect high redshift galaxies in large numbers, and its survey mode means it can cover the sky area necessary to characterize large-scale structure statistically. On the ground, the Vera Rubin Observatory in Chile is conducting the Legacy Survey of Space and Time, a 10-year program that will image the southern sky repeatedly in multiple wavelengths. Rubin focuses on the relatively nearby universe, but its statistical catalogs of galaxy positions will provide the low redshift context needed to connect Webb's early universe discoveries to the large-scale structure we observe today. Combined, these instruments will build a four-dimensional picture of cosmic structure. 3 spatial dimensions plus time. If the early universe contains a population of anomalously large structures, the combination of deep Webb pointings, Euclid's wide field, and Roman's infrared survey power will detect it within the next decade. If the structures are there in abundance, the standard model faces a reckoning that cannot be deflected by appeals to statistical rarity. If the surveys find that the Webb structure is genuinely isolated, an extreme outlier with no comparable companions in any other surveyed field, the standard model survives, bruised but intact. The decade ahead is the decisive window. The instruments exist or are being built. The question is sharp, and the answer, whatever it turns out to be, will rank among the most significant scientific results in modern history. Science is a method, not a destination. It produces progressively better descriptions of reality, models that match observation with increasing precision, but it has never claimed to produce final answers. Every major revolution in physics, Newtonian mechanics, quantum theory, general relativity, arrived because a prior model, perfectly functional within its known domain, encountered something it could not explain. The Webb structure is that kind of encounter, and the philosophical weight of it is worth sitting with, separately from the technical arguments about dark matter and inflation and the cosmological principle. For over a century, cosmology has been converging on a picture of the universe that feels, to those who work within it daily, like something close to complete. The major features are understood. The expansion history is mapped, the composition of the universe is measured. The origin of structure is traced back to quantum fluctuations in the first moments of time. The picture is coherent, precise, and extraordinarily successful at explaining almost everything we can observe. Almost everything. The gaps have been growing, the Hubble tension, the impossible galaxies, the axis of evil, the quasar grouping anomalies, and now, a wall of galaxies in the young universe that exceeds the allowed scale by a factor of 4. Each gap, individually, has an explanation: statistical fluctuation, measurement uncertainty, model approximation. The explanations are always available. They are not always satisfying. What the Webb structure contributes, beyond its specific technical challenge to structure formation theory, is a clarifying moment. A moment where the accumulation of gaps reaches a threshold that demands a direct response. Either each anomaly is explained away independently, requiring increasingly elaborate patches to an increasingly strained framework, or the framework is acknowledged to be incomplete at a fundamental level, and the scientific community begins the uncomfortable work of finding what replaces it. For humanity, the stakes in that choice extend beyond academic cosmology. Understanding the structure of the universe at its largest scales connects to understanding where matter, energy, time, and space come from. Why the universe is the way it is, rather than some other way. Whether the physical laws that govern our existence are universal or regional. Whether the Big Bang was an absolute beginning or an event within something larger. These questions do not have immediate practical applications, but they define the frame within which every other question about reality operates. Getting the frame wrong means the picture inside it is misoriented, however detailed it becomes. Webb found something that does not fit the frame, and the response to that finding, how science chooses to absorb it, investigate it, and ultimately explain it, will say something important about humanity's maturity as a civilization capable of confronting the true scale of its ignorance. The standard model of cosmology has survived challenges before. In the 1990s, measurements of distant supernovas revealed that the universe's expansion was accelerating, something the standard model at the time did not predict. Cosmologists responded by adding dark energy to the model, a modification significant enough to redefine the universe's energy budget. The model was updated, not discarded. It absorbed the shock and emerged stronger, fitting the new data while retaining its core architecture. Could the Webb structure be absorbed the same way? Some researchers argue yes. The argument runs as follows. The particle horizon limit, the boundary that says two regions cannot be gravitationally connected if they are further apart than light has traveled since the Big Bang, applies strictly only to perfectly standard inflation with perfectly standard initial conditions. Inflation models with features, meaning specific energy configurations in the inflaton field, that produce enhanced density fluctuations at particular scales, can in principle seed large-scale structure beyond what simple inflation predicts. These are not exotic or fringe theories. They are studied actively and appear in the mainstream literature. If the inflaton field had a feature at a scale corresponding to roughly 1 billion light-years, the resulting density fluctuations at that scale would be enhanced. Gravity would then amplify those enhanced fluctuations into large structures faster than standard scenarios allow. The cosmological principle might still hold statistically, with the billion light-year structure being a rare but physically allowed outcome of an inflaton field with specific properties. The problem with this rescue is that it requires tuning. The inflaton field feature must be at precisely the right scale to produce the observed structure. Tuned explanations are allowed in science, but they carry a cost. Every free parameter added to a model to explain one anomaly reduces the model's predictive power elsewhere. And if multiple anomalies each require their own tuned explanation, the cumulative cost becomes prohibitive. The honest assessment, shared by a growing fraction of the community, is that the standard model is under genuine stress. The stress is not yet sufficient to declare the model broken, but the margin is narrower than it was 5 years ago, narrowing further with each new Webb result. What would force a true rewrite? Most researchers converge on a similar threshold. If systematic surveys of the early universe, conducted with Roman and Euclid over the next decade, find that large-scale structures at the scale of the Webb discovery are common, appearing in multiple independent fields at rates exceeding standard model predictions by factors of 10 or more, the model cannot survive intact. A framework that predicts 1 in a million finds 1 in 10 has made a fundamental error, and the error must be traced to its source. That source, whatever it turns out to be, will reshape cosmology. Webb's schedule is determined months in advance by a proposal process. Scientists across the world submit detailed requests for observing time, describing what they want to observe, why, and what they expect to learn. A committee evaluates the proposals and allocates hours on the telescope based on scientific merit. The competition is intense. Oversubscription rates, meaning the ratio of requested time to available time, routinely exceed 10 to 1. In the wake of the discoveries that have accumulated over Webb's first years of science operations, a specific category of proposals has risen to prominence. Deep spectroscopic surveys of the early universe at high redshift, targeting precisely the epoch where the structure and the impossible galaxies reside. Several approved programs are now conducting systematic spectroscopic mapping of early universe fields, attempting to build three-dimensional maps of galaxy positions at redshifts between 6 and 10, corresponding to the universe's first several hundred million years. The goal is to characterize the large-scale distribution of galaxies in that epoch, statistically, with enough objects in enough fields to determine whether the Webb structure is a population or a singular event. Alongside this, other programs are targeting the individual galaxies inside and around the structure, with deep spectroscopy, building detailed profiles of their stellar populations, chemical compositions and internal dynamics. These observations will constrain the age distribution of the galaxies, the timing of their first star formation, and the mass of their central black holes, all of which carry clues about the initial conditions that produced the structure. A separate set of programs is targeting the gravitational lensing signal around the structure, using the distortions in background galaxy shapes to map the dark matter distribution in 3 dimensions around the filament. This will determine whether the structure sits inside an extended dark matter halo of extraordinary size, or whether the dark matter follows the visible galaxies closely, with no hidden reservoir. And a growing number of programs are devoted explicitly to testing the cosmological principle at high redshift, measuring the statistical isotropy of galaxy distributions across multiple widely separated fields. If the universe's early structure is the same in every direction, these programs will confirm it. If it is not, the alignment of anomalies will begin to take statistical shape. Webb has changed the questions cosmology is asking. A telescope designed to confirm the Standard Model's predictions for the early universe is instead generating the most systematic observational challenge to that model in a generation. The structure that should not exist is now the center of an expanding scientific investigation, one that reaches backward to the first moments of time, outward to the edge of what we can observe, and forward into the most fundamental questions about why the universe looks the way it does. We found something in the dark that broke our map. Now we are building a better one. The universe is waiting to see if we get it right.